My name is Muyun Li. Here's my presentation. The topic is a centralized near-optimal overlay network for inter-datacenter data replication. To begin this research, because large-scale online server providers such as Google, Facebook, Baidu, there have many important data communication patterns. Some also bank data transfer, that is replicating massive amounts of data from one source database to the destination source database. This server include user logs, web search indexes, and photo sharing blog posts, and so on. As before, things are not very difficult when there are not many data centers. Just replicating the data from the source data center to the destination data center. However, these large-scale online server providers always have hundreds or even thousands of data centers. So such a simple data replication schema is obviously not efficient because the upload link of thousands data centers will be the bottlenecked. Intuitively, the performance of introduced multiple cases would be substantially improved by sending data in parallel. For example, in the first cycle, data center A sent different blocks to B and C, respectively, and the second cycle, B and C exchanged the blocks, and A sent the rest blocks to them. Such solution avoids bottlenecks of the source data center by using the overlap path A to B to C, and otherwise it was A to C to B. This improves the replication efficiently. This is path bottlenecked destroying overlay. They don't need to share a common link and to to fight the potential for leveraging such as the bottleneck destroyed overlay path. Here is a typical example. First, setup and topological. Suppose we need to replicate the 36 gigabit data, which is split into 6 blocks from data center A to B and C. There are two paths. The first is from A to C using IP layer 1 routing with 2 per second capacities, and the other path from A to server B in data center B with 6 gigabit per second capacities, and then from B to data center C with 3 gigabits per capacities. And the simplest strategy is to make this direct replication, and the completion time is 18 seconds. The second strategy is to make a simple training application. We use application overlay path to send blocks to route through server B, asking a store and forward a point. Placed in this schema, the conversion time is 13 seconds. So there is another strategy. We call it multi-case overlay using this bottleneck disjoint overlay path. And this lets selectively some blacks using two bottom links joined over a path. And in the first cycle A, send 3 blocks to B and 1 block to C. And then B send 3 download blocks to C and A. A sends a rest 2 blocks to C. Such schema complete the replication in just 9 seconds. This example gives us a key that a Inter-Datacenter could be substantially improved by sending data in parallel while bottleneck destroyed overlap paths. So, what's the bottleneck disjoint over the path? We define it as two paths that don't share common link or intermediate server in the context of dictated data. Transfer there are two kinds of bottleneck disjoint overlap paths. The first one is two paths that traversed different sequences of data centers, like the priori example shows. And the second one is two paths that traverse different sequences of servers of the same sequence. The data center, just like the example we introduced, which completes in just 9 seconds. Using an efficient enough control logic for the basic communication, beneath the following parameters as input, such as data blocks and scheduling circle and the link capacity. In each schedule links circle, BDS returns two tuple as output. We select the first one is whether server is selected as the transmission destination server. How much bandwidth we could allocate to each transformers. Of course, such formulation have multiple constraints. So, for example, the constraints on local bandwidth and link capacity in transfer blocks and scheduling circle. These constraints makes the formulation incredibly in practice because it is superlinear and mixed integer. So the computation overlaid groups essentially with more potential source server and data blocks. A scheduling step which selects a subset of blocks to be transferred in each circle followed by a subsequent routing step, which is picks the path and allocated panelist to transfer to the selected blocks. So take the previous scenario as an example. Select a subset of the blocks to the transfer in the circle. This is scheduling step, and then pick the path allocation bandwidth and execute the transmissions in the routing step. And then here's another scheduling step and the transmission in another routing step. Such significantly a strategy could be better. So the certain space of the routing step is significantly reduced. As the implementation, there are three main components of BDS: agent, controller, and monitor. It starts with agent locally. on each server and checking the local states and report the states to the centralized BDS controller via agent monitor. The BDS controller also receives network levels statistics from network monitor and then runs the centralized decision-making logic to work out new scheduling and routing the decisions and the scenes. Finally, the agents carrying out actual data transformed according to the controller decisions. And these figures show the details and the CDF of the computation times on each destination servers. Of course, lower is better, and from these figures, we can see that BDS consistently. We see that BDS achieves three times shorter computing time than that Bullet and Akamai in the basic lines set up and even over 4 times shorter commute time in the larger scales and small bandwidth setups, which shows that BDS has greater improvements in extreme cases. The left figure shows the running time as a function of the total number of the blocks. To put this figure into a perspective in Baidu data centers, the maximum number of the similar blocks is around 300,000, for which BDS can finish the coating within 300 microseconds. The figure in the middle shows the network delay over 5,000 requests. We can see that 90% of the network delay below 15 microseconds, and the average value is about 25 microseconds, which is less than 1% of the decision updating cycle. The default cycle is 3 seconds. The red figure is the delay of the whole process. In most cases, over 80%, and the feedback loop is lower than 200 microseconds. To sum up, we can claim that BDS demonstrates a shorter enough latency and is able to scale to even large systems. Here, that's all. Thank you.